some of the stuff that you see, okay, you may not think it's related to the real world, but that is probably because we may deal with it in a very simplified manner here. But, okay, in reality, okay, it is actually the basis for many phenomena that you will observe. Okay, so we are going to start. These next 4 lectures will be on acid-base equilibrium. Another 3 more will be on solubility equilibrium. Okay, so I will start with showing you a little bit about the real-world effects of acids and bases. Okay. Okay, so you are familiar with acids and bases. If I ask you to name an acid, you can be able to name, let's say, hydrochloric acid, nitric acid, okay, sulfuric acid. Some of you who read a little bit more will be able to tell me the name of vitamin C, which is ascorbic acid. Okay, the bio students will be able to tell you the A of DNA is acid. It's a nucleic acid. Okay? Now, let's talk about some real life things about how acids and bases can affect you. Now, basically, if you are a healthy human, okay, I'm sure you know what arterial is. It's a blood that is pumped out from the heart. Okay, the blood pH should be, it's actually a very narrow range. It's between 7.35 to 7.45. If it falls below 7.35, that means the blood pH is too low. You can actually die from this. Okay, which is why I'm bringing it up. Okay, I'm quite fascinated with things that can kill you. Okay. However, it is not as simple as things. If you're a student like me, you say, okay, so if I want to kill Mr. Azmi, I shall offer him a glass of lemon juice. Then it will become too acidic and then he'll die. Nelson, don't smile, I know you're thinking it, and it's not going to work, okay? Okay, you will learn later on why you cannot simply do this. This effect, acidosis, is usually the effect, one of the symptoms of a very serious diseases, and there are a lot of them. Diabetes is one of them. Okay? The other one is the opposite. The blood has become too alkaline. Okay? Now, the bio students will understand this better because you deal a lot with the difference in the potential. Let's say the proton, H plus potential and so on, which H plus is the acid. So changes in the pH of the blood, okay, and therefore in the cell fluid can result in irreversible cell damage. Okay, there was an old movie, okay, old by your standards, starring Tom Cruise and Jack Nicholson, which you all will think as old actors now, but that was when Tom Cruise was young and handsome. Okay, called A Few Good Men, and the basis of the story was there was someone who died. Okay, and he actually was suffering from one of these conditions. The blood pH was too low. Okay. Okay, more common thing you have seen, this would be like something like acid rain. Okay, usually cause you won't see it around Southeast Asia because this often happens in very heavily industrialized countries where they burn coal, and therefore there is a lot of sulfur dioxide and nitrogen oxides in the air. And the effect that they see is that the trees die off. And probably a second effect is that when they die off, then forest fires can start more easily. Okay? Okay. Another effect of acid rains affects places like Greece. Okay, in the Mediterranean, they probably a lot of the buildings and the temples, the historical buildings were made of marble. So like the statues. People travel all from all over the world to see it. However, once the industrial age began, then you need to think, what is marble? Marble is calcium carbonate. Carbonates react with acid. And so over time, these monuments have been damaged. Okay? Okay, so there are countless other examples I can give you. Okay? But let me, before I forget. Okay. This it's a website called New Scientist. There's a lot of stuff here. You can go and explore. I just want to let you know we actually have a copy in the school library. You can go and take a look. Okay? Because I think all this background information is actually important for you to understand the relevance of the subject that you do. Okay? And it's for all three sciences. Alright? Okay, so ionic equilibrium in a way is related or subset of chemical equilibrium. Okay? So they arise because they are reversible reactions. So the first one, I think you know, sulfur dioxide plus oxygen to give you sulfur trioxide. Second one is an organic reaction. You have ethanoic acid plus methanol to give you what we call an ester plus water. Okay, so you will need to remember the concept of an equilibrium constant, Kc. I stress it's a big K. And you will need to know the Chantelet's principle, which today, some of the classes we have done it last week, and beginning today, some of you will be trying out this in the lab, hands-on activities. Okay, so you need to understand these three things well. Okay, so ionic equilibria we will divide into two main sections. Okay, for the purpose of lecture, there's acid-base equilibria. Okay, under that we'll cover the weak acid, weak base dissociation. We'll cover salt hydrolysis. We will cover buffers. Okay. Solubility equilibria will be another 3 lectures, and then we will cover sparingly soluble salts. Okay, it's a simple enough concept, but it's a bit mathematical, so you need to understand that. That's why it's going to take 3 lectures. Okay. So, what are acids and bases? It's a seemingly simple enough question. So what's an acid? What's a base? Okay, you can name it, but the thing is, are you able to define it? And over time, the definition has actually changed. And when the definition and the theory has changed. So, the earliest theory that we are going to make you learn is the one that probably you are familiar with. Okay, Arrhenius theory of acids and bases, 1884. Okay, you will think about acid produces H+, bases produces OH-. There's a Bronsted-Lowry theory, okay, which is in terms of again in terms of H+, and there is the Lewis theory of acids and bases, where it is in terms of electron pair. It dispenses with the idea of the H+. Okay, so 1938. I think this Lewis is the same guy that did the Lewis diagram. Okay. So, Arrhenius theory of acids and bases. So, anything, a compound that dissolves in water to yield H+ is an acid. Okay, so I think this theory, everyone know, all of you know, okay, and you're familiar with it. Okay, a base is a compound that dissolves in water to yield OH-. Again, you know it. right? So NaOH plus. Okay, when they say plus AQ, okay, in the notation means it means dissolved in water, plus water. Okay, so you may want to take note of that. That is what the equation is saying. Okay, HCl plus water to give you H plus Cl minus. Alright? Okay. Now, in general, why do they move on from a scientific theory? It's because the previous theory, okay, had problems. So, limitations of Arrhenius theory. So, because of the thing about you must have H plus, you must have OH minus, this is going to restrict it to reactions that occur in aqueous solutions. Okay? There are many acid-base type of reactions that occur in solvents or maybe even with no solvent. Okay? So, if you get HCl gas and ammonia gas, they will actually react to form ammonium chloride solid. Okay, I'm not sure whether you will have done this in QA for in year 4, because this used to be a common test for ammonia. You take a glass rod, you dip it in HCl, you bring it near to a test tube that is, and inside there is ammonia gas being evolved, and suddenly you see a dense cloud, okay, of white, and it's actually what you think of as smoke. They're actually tiny crystals of ammonium chloride. Okay, so they say a dense white smoke. Maybe next year when we start doing QA, we will show it to you. Alright? Okay, now, the other problem is by defining the base as something that produces OH minus in aqueous solution, you cannot explain things such as ammonia and amines. Okay, because those are considered to have basic properties also. Okay, the theory focused on the existence of this hydrogen ion in H plus, okay, in aqueous solution. But when the scientists really started thinking about this, they realized this is a problem. If you think about it, H plus alone is just one proton. That is a very small particle. And the charge density, if you take is a charge over the radius. What's the radius of a proton? It's extremely small. Okay? It will be very high. So this H plus ion cannot really or doesn't really exist in aqueous solution. Okay, later on we'll talk about what actually does happen. Okay? So what it turns out that the H plus, okay, is always going to form a dative bond with a water molecule, and what exists is actually H3O plus. Okay? How many of the bio classes here are D and E, right? Right? C is not there. Yeah, so you guys, when they talk about all this, when they talk about particles, the size of that, you must bear this in mind, because whenever you talk about things passing through membranes, there is going to be a certain size channel in the membrane. And this is what happens. Okay, this is how they can regulate it. Alright? Because if you just talk about the H plus, the proton itself, it's so small it can pass through anything. Okay. Now, more up-to-date Bronsted-Lowry theory of acids and bases. Okay, so now they just think of it, okay, let's dispense with the OH minus. An acid is anything that donates a proton, a base is anything that accepts a proton. Okay, so H plus, the proton is H plus. So for example, HCl plus ammonia, we can give you ammonium chloride. Note that because they define in this way, you don't have to have water present. Okay, it can take place in any sort of solution. Okay, if you look at it, as long as you see this transfer of the H plus, you can say that it's an acid, or you can accept H plus is a base. Okay, so HCl, it donates the proton to ammonia, so NH4 plus chloride. The Cl is a spectator ion. Okay. So this one is ethanoic acid plus OH minus. The ethanoic acid donates the H plus to the OH minus, and then you get water. Okay, so the OH minus is this. Okay, so go and quickly try it. The last one, you really need to think of the definition. Okay, for the last part. Okay. Now, first one, I think okay. It's Arrhenius theory in HNO3 is an acid. Second one also it's fine. Nitric acid plus NaOH to give you sodium nitrate plus water. Nitric acid is an acid. Now, I want you to remember this. For A levels, right, definitions are important, and it's important for you to understand, not just remember the definition, because they can use it to test you on something unusual. If I were to ask a year 3 or 4 student, nitric acid plus sulfuric acid, which add together, which one is an acid? The term is ethium. Both are acids, right? But by this definition, you need to look at the product and you need to see what happens. So, which is the one that accepts the proton? Which is the one that accepts that donates it? So, in this case, the proton went to the nitric acid, so it is a base in this case. Sulfuric acid, later on you'll learn about acid strength. Sulfuric acid is a stronger acid. Force the nitric acid to accept a H+. The interesting thing about this is, in this case, is the state symbol. Go and highlight it or underline it. Both are liquids. That means both are pure. What you see in the lab is not the pure acid, or there are solutions usually. They contain water. This one they are dealing with the pure concentrated acids, highly concentrated acids. Okay? Okay. So, as usual, there are limitations. That's why we have another theory. So, Bronsted theory, there are certain things that don't contain any hydrogen, but yet have properties that are acidic. So, for example, aluminum chloride and boron trifluoride, which you would have come across in chemical bonding. That's why we keep picking those substances to make you strong. Okay? And if you have done your tutorials religiously, you will start to think about why they can function as acids. So aluminum chloride plus ammonia. The ammonia can form a dative bond with the aluminum chloride. I feel like picking someone from my class to answer why they can form a dative bond. I see some people smiling. I shall not. But tomorrow I will ask you. Okay, so Lewis theory, acid is an electron pair acceptor, base is an electron pair donor. Back to our aluminum chloride and ammonia, can you think about this? Aluminum chloride, how many electrons around aluminum? Ammonia, does it have a pair of electrons to donate? Okay. So with BF3, boron is in the same group as aluminum. Boron is actually electron deficient. If you go and draw the dot and cross diagram, you will find that boron has only 6 electrons around it. Ammonia, the nitrogen has a lone pair, therefore you can form a dative bond. So here, the BF3 is the acid, the base is the NH3. Don't say, please don't go and say the boron is the acid. The whole thing is the whole compound, BF3. Neither is nitrogen the base. Okay, it's the whole thing. Ammonia is the base. Okay? Same thing goes for H2O, because then, remember, oxygen has 2 lone pairs. Okay, and there's aluminum chloride. Okay? These examples that are up here come up frequently in multiple choice questions. So it would be make your life easier if you can remember the structures offhand. Okay? Okay? Okay. And this one, the last one, I think you're quite familiar. H plus NH3 to give you NH4 plus. Okay? Okay. Now, what about this? Which is the acid, which is the base? So, Lewis theory, think in terms of lone pair of electrons. And for the base, all these things of the lone pair of electrons, does it have lone pair of electrons to donate? Or the acid, think of it, is it electron deficient? Okay? So, aluminum chloride is electron deficient. Chloride itself has 4 lone pairs. Okay, so it can donate 1, and AlCl4. Why we do this is this one, it will be, you may want to put no, okay, never mind, don't do it, because I think you will get confused, because there is a link to organic chemistry, but never mind, too far away. Okay, when we lecture organic chemistry, then we will remind you about this thing. Alright? Okay, so tetrahedral in structure, and there will be put a negative charge on there. Okay, next thing we talk about. Okay, so the summary, Arminian theory, results in water to give H plus. Second one, Bronsted-Lowry theory is just about proton donors, doesn't need water to be present. And third one, Lewis theory, you are talking about electron pair center. For base similarly, Arrhenius theory, talking about dissolving the water to get OH minus. Bronsted-Lowry theory, you're talking about proton acceptors. And Lewis theory is talking about electron pair donors. So, the contrast between the Bronsted theory and the Lewis theory is they are defined in terms the H plus and the electron pair are taken to be opposite. Would someone like to wait and sit down? Okay. Now, the next part, now that we have defined, learn about the definitions of acid and bases, let's talk about how do you know whether something is a stronger acid or base. Okay, so there are different ways of looking at it. And there are limitations to each method of seeing whether something is stronger or not. So, we will look at the degree of dissociation. We will look at pH and what it means, how it's defined. And we will look at the acid dissociation constant. Okay, this is an equilibrium constant, so it's capital K. Okay, capital Ka. As contrasted to the rate constant, which is small k. Okay, so there's an acid dissociation constant and there's a base constant Kb. Right? Okay. So, now whether something is a strong acid or strong base is determined by the extent or degree of ionization in an aqueous solution. So, if it's a weak acid or base, the ionization is partial. It's partially ionized in aqueous solution. So, for example, ethanoic acid. Ethanoic acid is the acid that you find in vinegar. Okay? The ionization is partial. So, most of it will be in the molecular form that you see on the left-hand side. A very little bit will ionize and produce the ethanoic ion and the H+. I want you to get this in your head from the start. You take vinegar, right? Very little of it is H+. Okay? Most of it still exists as a molecule, unionized. Okay? Ammonia and water. So you get the equilibrium with the ammonium ion and OH minus. Okay, so if I give you, say for example, 1 mole per dm cube ammonia, aqueous ammonia, then you, let's say you get the lab, something like that. You cannot tell me that it contains 1 mole per dm cube of OH minus. It does not. It doesn't contain very much OH minus at all. Most of the it will still be in the form of NH3 molecules. Okay, and it's in equilibrium. Okay, so consider weak acid in water only. Okay, the reason why we write H plus there, not H3O plus, is just to simplify things. It doesn't mean that the H plus really exists. So, if you look at the initial concentration, let's say the weak acid HA is 1, the A minus is 0, H plus. Okay? Let's say X of the HA ionizes, then you will get plus X for the A minus and plus X for the H plus, and then you get an equilibrium. So at equilibrium, we have 1 minus X for the HA and X for the H plus. Okay, so at equilibrium, forward ray equals backward ray. Wrong spelling for backward, sorry. Okay, so this is just to show you how they define. At